questions? Everybody's off and running? Okay. Well, if you don't have any questions, then we'll go ahead and launch into Chapter 2. And as I indicated on Monday night, we're not going to be quite so quick going through Chapter 2. Of course, you saw in the syllabus we have 2 lectures dedicated to this particular chapter, which is a very important chapter, as are all of them, actually. But Chapter 1 is sort of an overview, and for a lot of you, it should have been just review material, so you shouldn't really have too many issues with what we did in Chapter 1. Okay, but it's still testable, right? Okay. It's equally testable. But now we're going to go into Chapter 2 here and talk about processes and threads. And as you recall, this is really talking about the processor subsystem, how we're virtualizing it, and how we're creating mechanisms so that we can use and manage the CPU resource across multiple processes, right? That's kind of the end game here for what we're trying to do with the operating system. So what we're going to do is we're going to look at the process model. We saw a very, very simplistic one on Monday, but we're going to see a much more complex one here, which is much more realistic in the sense that it's embodying a lot of the different issues that we have to address as we create and manage and exit through our processes. We're going to look at the process structure. What this means is we're going to look at how processes are created and managed in memory, how we're going to use main memory to hold all these different processes as they go through the different states here. Okay, we're going to talk about threads, oftentimes referred to as lightweight processes. We're going to talk about some of the differences between threads and full-up processes and understand how those work. And then we're going to spend a lot of time talking about concurrency. Okay, and we kind of introduced some of those things on Monday night, but we're going to start digging down into the actual algorithms for concurrency and the mechanisms in more detail in this chapter. Okay? That's what we're going to do. So let's start off with the process model itself. And the process model, as we were hinting at here and already starting to introduce, is important because it's going to allow us to not only model the process so we can describe how it's made in memory and all that kind of stuff, but also what to do with the different processes when they're doing different things in the operating system. Okay? So to understand why we need that a little bit better, let's talk about sort of the life of some processes in a couple of different ways. Okay? All this is about multi-programming. I probably should introduce that first, right? We talked about multi-programming operating systems in Chapter 1. The type of operating system that we had before we had multi-programming operating systems were called?
Monolithic.
Monolithic, excellent. Okay, in the case of monolithic operating system, the application was compiled into the operating system itself, so we didn't really have to worry about concurrency. But here we do. Here in multi-programming operating systems, if we have 4 different programs that are running, which makes them processes, right? If we have 4 different programs that are running, we have several different ways we could go about making this happen. One way we could do this is by having processes switch when they complete all their work. So process A runs, then it switches to B, then it switches to C, then it switches to D, and so on, or whoever comes next, right? Another way to manage it, okay, that's one way, each process knows about the next one. Another way we can manage it is by having these things called program counters. And every process has its own program counter, because as you recall from your architecture days, there is in the machine exactly one program counter, right? And that program counter does what?
It keeps track of what a program is at the execution.
No.
It's the address of the next instruction.
It's the address of the next instruction to be fetched by the processor or processor?
Another process.
By the processor.
What's the
So,
difference?
what's that?
What's the difference?
What's the difference, he asks? Okay, so that's a great question because I need a caveat. I did introduce one more caveat here. We're going to be talking about multi-programming operating systems, which is talking about multiple processes loading and running concurrently. And And as you know, many many computers today have more than one processor on board. We're going to use the single processor model for most of our discussions. Our discussions will scale to multiple processors quite easily, but if we stick to a single processor model, then you can see how it scales much easier. So most machines might have 2 cores or 2 processors. That's fine. It's not going to work a whole lot different than what we're going to be talking about for the single processor model. So we have one processor in our machine that we're going to be studying. So one processor, but I have multiple processes. So the one processor has a register in it called the program counter, which contains the address of the next instruction for that processor to go and fetch. Now in this model here, what I'm saying is that, hey, I could have multiple processes, and each process could have a copy of its program counter. Because if it has a copy of its program counter, then I can actually stop A and start B, and it will know the address of the next instruction it needs to go and execute. I can stop B and let A run again, I can stop B and let D run. By giving each process a copy of its program counter, then I can switch between my processes like that. Okay? And so in that model, it would enable me to do something like this, where I could have processes that have long lives. When I say long lives, that is, they may not be batch, they might be batch processes with a lot of computation to do, or they could be interactive processes, which requires lots of input from multiple users, multiple processes, or from keyboards or other devices. Multi-programming operating systems typically allows us to create lots of these interactive processes, and that's what we see a lot of today are mostly interactive processes, although we still have some batch processes out there, typically supporting things like queries from the network and stuff like that. So we can have the situation here where process A may run a while, then it needs to wait for something, or be told to give up the CPU, and then it can run again, and then it can run again, and so on. In order for me to do that, then each process must have a copy of its program counter. It needs some other things too, but that's kind of the key thing here, is that we have the physical program counter register, and then we have these virtual program counters where every process has its own copy. Okay, next question? Excellent. Let's see, do I want to talk about that now? Interactive processes, no, I'll get to that. Okay, so that's how we kind of got into the, I need a copy of a program counter. So let's talk now about the life of this process. The first thing we're going to be concerned with is creating a process, right? It's kind of the first thing you want to do, is create a process. These are the events that can cause a process to be created. Obviously, as you are starting up your operating system, it's loading stuff into specific memory locations. We're going to take a look at that a little bit later. But at some point, it needs to actually start running its own processes. So you'll run its first process, and then it may start up some other processes, and so on. So operating system initialization, that should be an obvious one. Okay, then there's the fork system call. Any process running using the fork system call is going to create a new process. We saw that on Monday. Initiation of a batch job is really just the specific instance of creating a new process. User logs on, we walked through that on Monday. They're creating a new process, an interactive one in this case, right? Your shell processes are interactive processes, aren't they? Because what happens? What was that simple model of a shell? What did it say we were going to do in that simple model of a shell? We first print a prompt, right? And then what do? We wait for an input from the user, input from the keyboard. Once we get input from the keyboard, we parse it, fork that new process, print the prompt again, and wait for the user input. Life of a shell. Okay, it's interactive. User logging in is going to create that. Service providers, this is what I was just referring to, where I might have a network connection come in and say, hey, I need to have a job printed, or I need to do a remote login, or I need something else. Okay, you're gonna create new processes. You got iNet daemon sitting there waiting for a request from that port, and it'll create new processes to service those requests. And of course, you can double click on icons instead of typing things in. Your program also might make multiple fork calls because you might create several child processes that talk to each other to do specific tasks. Lots of different ways you can create a process, but they all boil down to there's some process running and it's gonna call fork, the system call to create new child processes, okay? All right, that's how we create them. How do they go away? Well, there's a normal exit, right? It's going through the code that the programmer wrote, and there's an exit system call. Normal exit. That's a good one. So other than that normal exit, we have two categories of exits. Okay, we have errors and we have faults. Errors and faults. And we'll come back and you can tell me which one's worse. Because there's some very specific definitions behind error and fault. Let's see if we can figure that out. But let's look at some examples first. Errors. I/O failure. Oops, you want to go read a file from a disk that got removed, that was removed from the file system. It's no longer there. You're going to get an I/O failure. Or somebody hit the power down switch. It was an external drive or USB drive. Somebody unplugged it, tripped over it, turned the power off, whatever. It's no longer there. Data misuse, program's parent terminates. That's a special case because you can actually, I'll talk about that later, never mind. So let's say a parent process terminates. When the parent process terminates, in the normal configuration, it will also kill off all of its children. Okay. Yeah, there's some problems with the models that we use to describe processes and childs and stuff like that. Don't take it too personally, okay? Parent dies, is taking his children with you. Oh, yeah. It's not exactly like life, hopefully. Okay, so that's one way. Another way is that the parent process can signal other processes to terminate. Those are what we call error exits, okay? Faults. Okay, faults are things you can't recover from. You can recover from these. As a matter of fact, when you are working on your assignments, you're checking for these kinds of errors and you are going to handle them. Okay, whenever you use a system call in our assignments, you should always be looking at the return code, and you're going to catch basic errors, and you're going to, of course, catch good returns as well. Okay? But I expect you to find basic errors and handle them gracefully, because that's what we can do with errors. We can say, oh, I couldn't open up that file because that file system is missing. Okay, I'll just let the user know that it's not there, choose another, right? Instead of saying, oh good, I'm done. No, you can handle those. Faults, however, are things we can't recover from. An invalid instruction. How can an instruction be invalid? Did the compiler generate an invalid instruction? I know you probably would like to think so because it actually rejects some of your syntax in your programs. So obviously the compiler is flawed, right? And it might generate a bad instruction? No, it's not going to generate a bad instruction. You're going to get an invalid instruction because something happened in memory. Something bad happened in memory. And if something bad happened in memory, do you want to continue using it? Who said yes? No, don't, because you can't trust anything else at that point. So that's a good way to tell you that there's something corrupt, something wrong, and you need to shut down and restart those. All right, good friend, the divide by zero, you know about that one. Try to execute data. This is kind of in the same vein as our instruction. Okay, if we get a bad instruction, or if we're actually in a data region and we're trying to execute data as if they were instructions, you know, we're going to get invalid instructions, or it might actually be a legal instruction, but it's going to cause you to do something horrible to some other memory location or to the hardware itself. So we don't want that to happen. That is very, very bad. Privileged instructions when you are not in the CPU privileged mode. Another bad thing. Also, the operating system itself can actually go in and clobber your process. Okay, that's a fault. You're not going to recover from that. And something called deadlock, which we're going to study towards the end of this chapter. All of those things are faults. All of those things are non-recoverable. All of those things we want to shut down and go away. Okay, and then make the user restart it, or debug it, and then restart it, because something really bad happened. But it might not have been bad code. It might be somebody had actually hacked your process, or there's hardware is going south, or something bad is happening, and you need to go look into it instead of continuing to run. Okay, so faults, non-recoverable, don't want to try. Errors, we like those, because there are times when things happen and we can respond to it. We being the programmer user, right? In most cases. So the programmer user might provide the end user with some tools to maybe select another file from another file system, or go mount the file system, or something that allows you to do that. Okay, so we got creation and terminations of processes. Any questions so far? Okay. Then I'm going to just jump right to the Unix model of a process transition. Now, I vary from your textbook here because of two reasons. One is that this is a real model. The stuff in your textbook is notional. And what your author likes to do is start with little baby steps. Oh, look, here's a 3-stage model. Oh, look, a 4-state model. Let's just go right to the 9-state model, okay? Let's see if we can follow this. Okay, in the beginning there was fork. Fork happened, we created a process. So we go into the create state to do that work. Once we've created the process, oops, we've got to figure out, did we get created in memory or did we get created in swap space? If we got created in memory, let's take this one because we're always optimistic. If we were creating this process in memory, then I would transition to the ready in memory state. Now, when you are not in the run state, the ready in memory state is the place to be, okay? Because that's where you get selected to go back into run state next, okay? And only one process may be in its run state at any time. Again, the model of a single processor computer. If you have 2 cores, you'll have 2 in the run state and so on. But for the one processor model, okay, there's only going to be one process in its run state at any given time. All other processes are going to be in one of these other states. Okay? So if you're not in the run state, this is the place to be. Because in the ready to memory state, we actually have a queue associated with this, as well as some other states. There's a queue in here called the ready queue. If you are in the ready in memory state, your process ID is put into that ready queue, which is basically a FIFO queue. And when you get to be at the head of that queue, then you're the next one selected to go into the run state. Yee-hee, go to run. So selected to run. You go into the run state. Now here is something very, hopefully interesting, but it's certainly non-traditional for state modeling, right? State process modeling. Okay, because I kind of took this one state and I blew it up into 2 sort of half states. Because what happens is when we're in the run state, we really have 2 states we could be in. We could either be in the run kernel mode state, or privileged mode, or exec mode. Each CPU manufacturer has their own name for that privileged mode. So we'll call it run kernel mode. Okay, so we'll initially transition to this state, so it will have the privileges it needs to access protected parts of the operating system. More about that later. Once it's done all of that administrative stuff, it will then transition to the run user mode state. Okay, putting the CPU into user mode and start executing your instructions that you programmed it to do. If you decide to use a systems call or something else happens that we'll come to later, and your process needs to go and pretend it's part of the kernel, then it's going to transition via this interrupt or system call to the kernel protected mode, that's the kernel mode, so it can access the protected stuff, and do whatever that system call told it to do, or handle the interrupt as needed, okay? So it'll transition back and forth between the user mode and the kernel mode, so it can either do operating systems type of work, or it could do your work that you programmed it to do, okay? And then what's going to happen here is that if your system call says, I need to wait for some, like an I/O device to deliver some data. Let's say, for example, you opened a file, or you want to read or write to a file, okay? You're in the CPU. Things are happening very, very fast. I/O devices are very, very slow, right? So what's going to happen is, if you're blocked on that read or that write or that open or that close, if you're blocking on that system call, then what's going to happen is you are going to transition yourself out of the run state. Okay, you got to get the kernel first, so you transition yourself to run state, and then you transition into blocked in memory state. Okay, so you are blocked for this I/O event to complete. This read, write, open, close, whatever it happens to be. Okay, so that's one way to get in here. Another way to get in here is that you may have hit what we call your time quantum. In order for our multi-programming operating system to be effective, it has to give all processes a fair and equal chance to use the processor. So what's going to happen is some processes, and I'm kind of jumping myself ahead a little bit, but I need to introduce it now. Some processes are what we call I/O bound processes. That means they do a lot of I/O activity, which is very slow stuff, and not too much computational stuff. Okay, so if they're doing lots of I/O stuff, that means they're going to be doing lots of blocks. Okay, and typically these will happen frequently enough that this process will give up the processor plenty of times so that other processes can have a chance to work. But some problems are not so much I/O bound, but they're processor bound. They're very computational. And they don't have a whole lot of I/O activity, but they do a whole lot of computations. And if we let them just run from beginning to end, then I'll have one process running, and I'll have the other 59 of you sitting there saying, is this machine still running? Is this machine still running? I don't know. I'm not seeing anything happen here. Is this machine running? I don't know. But this one process here is really happy. Okay, so that's not too cool. So what we're going to do is we're going to implement this time quantum for every process. And what that time quantum is going to do is essentially enable this to happen. It'll say, I'm going to give everybody a slice of the CPU, and then they have to give it up to somebody else, then they have to give it up to somebody else, and then we'll come back and let them do some more work after everybody's had a chance to do some work. So whatever that time quantum is, 50 milliseconds, whatever, whenever your process goes into the run state, it initializes that time quantum. And so your process will run in the run state, going back and forth as needed here. And if it doesn't block for some I/O activity, then what will happen is when your time quantum expires, that's an interrupt. The time quantum will interrupt the process. You'll go into the kernel mode here, and in the kernel mode, it's executing some kernel instructions saying, oh, this interrupt was because of time quantum. You have to transition out of the ready state. You have to transition out of the run state. Okay, so the process will then block itself, select the next process to run, transition out, and transition that process in, and now it's in blocked in memory. Make sense so far? Okay, so now here we are blocked in memory state. Only one of two things can happen while you're here. You could be determined that it's going to be a long time before you get to go into run state again, and I've got other processes that need the memory and make you go to what we call block swap. Now block swap, the only thing that's different here is that you're still in the blocked state, except that we're no longer keeping you in main memory. We need main memory for other processes. So we're going to take you out to what we call a swap partition. We'll move the contents of your process from main memory to the swapped memory out there on the disk drive. So it frees up that main memory for some other process that's about to go into the run state. So from either of these states, you can transition into ready in memory or ready swapped once your event has been acknowledged. In other words, if you are blocking, waiting for a read operation to complete, when the read operation from that particular drive is completed, it would generate an interrupt. The current process that's running would say, oh, this interrupt belongs to this process, transition them from block to ready, or transition them from block to ready, and then you go back doing your work. That way you can go to the ready state. Okay, so once you're in one of these two ready states, then you're just waiting for your process ID to get up high enough in the ready queue so that you can then swap back into main memory. Somebody else has got to swap out. So you can swap back into main memory so that when you get to the head of the queue, you get to run again. And you just keep doing this and doing this and doing this until you're ready to terminate. You either have the exit system call that you ran, or you had a fault or a failure, right? In which case, you process it, because you're in the run state, you process it, you made that system call, or you're responding to an error condition. And then what you do is you hit the zombie state, where you clean up all of the memory and all the files and all the IPC mechanisms you were using. You clean up all that stuff, you give it back to the operating system, and once you've done that, then you fully exit the system and you no longer exist. Yes?
I'm a bit confused. After blocked in memory, you swap to block swap. Why do you do that? I'm sorry.
So if you're in this state here, and the operating system decides at this point that it needs more memory for a process that's about to run, then it's going to go look for processes here that it can say, I need some main memory and I need you to swap out. Go to the swap space on the large disk. So it frees up main memory in the operating system for these processes that are about to run.
Right. Okay. So it's just a queue, pretty much.
Well, it's a queue, but it's more than that because there's memory. I'm pulling it out of main memory and I'm putting it into this swap partition.
Okay.
And so if you're not, for those of you who aren't familiar with the swap partitions, the way they work is that in your in your disk system, and your disk system could be a spindle-driven mechanical hard drive, or it could be an SSD. I don't care. It's the same thing as far as this is concerned. It's still going through a bus and a port to get to that particular device. So in your disk system, you have a file system in here. And in your main partition, you're going to have a special file in here called a swap file or a swap partition in some systems. This is reserved for use by the operating system for this specific purpose here, so that it can swap processes out of the CPUs, out of the computers. Remember our computer when we had CPU, I/O, and main memory, right? So your processes are all in main memory here, except that there's not enough room in main memory for all of the processes to be loaded for real all at the same time. So what we're going to do is we're going to divide your process up into some different regions of memory. We'll take a look at how we're going to do that here in a later slide. But to help you understand this question, you need to understand that what we're going to do is we're going to divide up our process into several different partitions. Most of the memory required by your process, we can take and swap out into the swap partition as needed when we're in this state here. Then as your process is getting closer to being selected to run again, then we need to pull it back out of swap space and back into memory, so that the entire process is now sitting in main memory, ready to execute when it goes to the run state. That's why we have to be concerned with these two swap states here. Does that make sense? Other questions? Okay, the state model is a big deal. Hint. Okay. You should be able to describe it just as I did. So, hope you took good notes. Ask more questions if you have more questions. Since you think you got it, we'll go ahead and move on. Okay, let's look at these queues a little bit more detail. Okay, I've mentioned the ready queue, and I said that we had some others as well, but the ready queue is very important to the process state model, so that's why I want to make sure we mention it there. But the thing we're concerned with, because I very carefully stated that when a process is blocked in, when a process is blocked, either in memory or blocked in swap state, it's waiting for an event to be generated to say that whatever it was blocking for has been completed, right? And then I also said that it's up to the process in the run state to determine when that event comes in, which process in the wait state, in the block state, gets to transition into the ready state. So in other words, it's up to that running process to be able to map that event to the process that's blocked for it. And so you're sitting there saying, I know how to do that, right? Okay, so I didn't think so. So that's one of the questions you were probably thinking about, but you just didn't know quite how to ask it yet. So let's ask that question now. How does that process do that? Well, we do that by having these queues. Okay, the ready queue, we'll talk about that at first because that's the one that we looked at on the last slide, is pretty obvious. I have a process that's either blocked in memory or blocked in swap that's in this ready queue, right? And I have a process that's running, and when it's ready to exit the run state, either because it's blocking itself or it had some event like, oh, its time quantum elapsed, that caused it to say, I've got to transition states. So the way that the running process is going to know what process to run next is that it knows where this ready queue is. So all it has to do is look at the head of the ready queue, and that's the process ID inside of there of the next process to get to run. Okay? And so it will select that process, and then it'll give it to the processor, and off it goes, having a good time. Okay, so that's the easy one. There's some other work it needs to do too. We'll talk about that more a little bit later in the chapter. But that's how we're going to manage moving processes through when it's only the running process that gets to decide. Okay, now I've said this several times too. I know I'm stacking several concepts on you here without completing them yet. Bear with me. If I lose you, let me know. But another thing we have to be concerned about here is this fact that I keep saying the running process. And then the running process has these two states or pseudo states. There's the run state, there's kernel mode or user mode. And I'm always talking about the process doing your work, although it's going to be in this kernel mode, but it needs to do some system stuff. So does the operating system process ever actually run? Is there an operating system process? Yes?
Changing your password?
Nope.
No.
Yes?
What about, yeah, like your entire GUI runs on its own thread, for example. Like the desktop environment really runs on its own thread, so all that has to run too.
GUI's not your operating system.
Well, it's program application that sits on top of yours, but like the kernel is resident in memory, so those things have to run too.
There are some kernel functions. We did talk about that on Monday.
Yeah.
The kernel functions will be embedded in one or more processes, typically more. There is a process that in a microkernel type of operating system is the OS. However, since we are using this kernel operating system, we're using this multi-programming concept, what we are doing is we're actually building in parts of the operating system into every process that runs. Every process that runs is going to have part of the operating system in it. So therefore, every process that's running is going to know how to select the next process to run. So when you built your Hello World program for the very first time, compiled it, you were so excited because it ran and did things, right? Remember that? It's only, what, 4 years ago? 107 class? So that was pretty exciting. It did stuff that you didn't think you told it to do, right? Like how to actually talk to your terminal, how to actually listen to your keyboard, how to interact with the operating system itself. If you were in a windowing system, how to get the input output to that particular window in your windowing system. It did all that for you. Because every process is going to, in the multi-programming operating system, it's certainly a layered one, certainly not layered, but a kernel-based one, is going to have part of the operating system in every process. Let me ask you this question. When you wrote your Hello World program or some simple short program, and it contained, I don't know, maybe a dozen to maybe 100 ASCII characters in it, right? And you compiled it, and you happened to look at the size that resultant file and saw it was 32 kilobytes, right? And you wondered, of course, how did I get from a few bytes of data to this 32 kilobyte sized file? How many of us wondered that when we saw that? Come on, be honest. Really? Okay, go do it. Do your Hello World program, compile it, tell me how big that executable file is. It's more than the 100 bytes or whatever you had. Because the compiler, remember that last slide we had on Monday night was said the life or the architecture of C, right? The compiler included in live.a.c and live.a.a from that archive file, it created a whole bunch of operating system code inside of that process, the program file, in addition to your code that you wrote. It's all in there. Things about, I know the life of a process. I know the state model of a process. I know where different parts of me are going to be put into main memory. I know how to find the next process. I know how to respond to an interrupt call. I know how to respond to my systems calls. It's grabbing systems calls that you use, the object code for that, putting it into this executable file that you created. The compiler is doing all of that work for you, so it can create this process that can do your work, but also do some of the work of the operating system. Because that way, and only in that way, can we have processes running that can handle some of these quick interrupts and service them without having to do a full, what we call context switch, to an operating system, an over-encompassing operating system process to do all that work for us, and then give us the CPU back to our process. So that's how we're doing this in Unix and Linux systems. By making every process contain parts of the operating system within it. And of course, that means we have to protect it from you, because we know what programmers try to do when they have that much power, right? So we've got to protect all over the place. If we're going to give your process that you are compiling operating system code, we've got to protect that from you so that the system can work. Okay. Descope. Back down to this model. So now we talked about our process handled the RAID queue. It knows how to select different processes. It knows how to interrupt. Now what it doesn't know, because any process can be running when your process event comes in. So what's going to happen is we're going to create these event queues. An event queue for every type of event or I/O device that could be attached to this system. We're gonna create an event queue for every one of them. So what happens is, if your process is running, and it's trying to do a read operation from disk on USB 0, I have an event queue for USB 0. I will put my process ID onto this queue with my event. I'm waiting for a read event back from USB 0. So it's sitting here on this queue. There may be some other processes that are doing reads, writes, opens, close, whatever. And what's going to happen is the I/O device is going to, and we'll talk about that later when we get to the I/O subsystem. But the I/O device is going to do their operations first, and then when they're done, they're going to raise that event up so that the process that's currently running can say, ah, this event is now mapped with the process ID that's in this queue here. Go grab it from the block, from whichever state blocked memory or block swap, and put it into the ready queue, and then the next one can be dispatched and off it goes. That way the data that came in, sitting in a buffer somewhere with your process ID identified to it, and your process is now back into the ready queue, so it can run again and use that data.